Hi everyone, we're starting our new chapter, chapter 4 from the MYP4 text on radicals. But before we actually get started on that, I'd like to just go over very quickly the review on the real number system. So the real numbers are divided up into either rational or irrational numbers. So as you can see, the rational numbers are symbolized with a Q, which stands for quotient, which means that they can be written as fractions, or it's a form of division. And they are usually terminating or repeating decimals. So for example, 1/2 equals 0.5, 1/3 is like saying 0.3 repeating, and the square root of 16, for example, is a perfect square, and its answer is 4. So those would be considered rational numbers. Now the irrational numbers are numbers that cannot be written as fractions, and they're usually non-terminating or non-repeating. In other words, they can go on forever, but they don't have a pattern to them. So an example of that would be something like the square root of 5, which is equal to 2.236067, and that decimal would be going on to infinity, but with no particular pattern. And then of course we have the number pi, or the symbol pi, which is 3.14, and it has an infinite number of digits that follow, which again are not in any particular pattern, found in any particular pattern. Now before we start anything, I just want to take a quick look at the number line and where are certain numbers found. So for example, if I was looking for the square root of 2, the square root of 2 is going to be between 1 and 2. It's just a little bit bigger than 1, but less than 2. Same thing with with root 3. Root 3 would be between root 1 and root 2. And the square root of 4, would be between 1 and 2. The square root of 4 would be found exactly on 2, because the square root of 4 is 2. The square root of 5 would be just slightly over 2 units, and the square root of 16, for example, would be 4. So that means that if I were to go to the square root of 18 or the square root of 19, for example, those numbers would be between 4 and 5, just as the square root of 17 is between 4 and 5. Now the only reason I do this is that so that you have some acquaintance to where those numbers would be found on the number line, because we tend to see the square root numbers as if they're these sort of magical, sort of mysterious numbers, but essentially they really are found on the number line. Okay, so moving on, as I said, radicals are radicals like the square root of 4, the square root of 9, the square root of 16. These are all perfect squares. They are considered to be rational, as we saw on the previous page, because they're perfect squares. So the square root of 64, or the square root of 49, which are 8 and 7 consecutively, those tell us that they are rational numbers. But radicals like the square root of 7, or the square root of 5, or the square root of 21, they're considered irrational because they have decimal expansions that are either non-terminating or they're non-repeating. So irrational radicals also have another name. Irrational radicals are known as surds. So radicals would be root 4, root 9, root 16, all the perfect squares. Those are the rational ones. So root 16, root 25, root 36, root 49, root 64, root 81, and so forth. Okay? All the perfect squares are considered rational, and they're perfect squares, and they're radicals. And the irrational numbers like root 5, root 7, root 23, and so forth, those are irrational radicals that are known as surds. Okay. So our goal in this lesson today is to be able to write radicals in their simplest form. So what that means basically is that if I had, for example, the square root of 48, I want to be able to write the square root of 48 in its simplest form possible. So into its simplest numbers where I have prime numbers that are involved in it. Okay? So let's, for example, take a look at the square root of 48. Now, if I take the square root of 48, I'm going to find all the factors of 48. And I'm going to place all of those off on the side here. So I can start with root 1 times root 48. That gives me 48. And if I did root 2 times root 24, that would also give me root 48. If I did root 3 times root 16, that would give me root 48. Root 4 times root 12 gives me root 48. And then root 5 doesn't. Root 6 times root 8 would also work. And I think that pretty much covers all the possibilities. Now our goal is to find the highest perfect square in these different factors or combinations of factors. And the ones that have perfect squares on them are this one, root 4 times root 12, and also root 16 times root 3. Now because root 16 times root 16 is a higher perfect square than root 4 times root 12, then I'm most likely to choose root 16 times root 3. And in doing so, I discovered that the square root of 16 is equal to 4, and what's left over is a multiplication with root 3. So we just have 4 times root 3, which we normally just write out as 4 root 3. Okay? Now, that's not to say that I couldn't have used the other forms. I could have, but they just would have been lengthier to resolve or to solve. So let's just do a very quick example by taking the square root of 2 times the square root of 24. If I take the square root of 2 and the square root of 24 as an alternative, I could write root 12 times root, I had said root 2 times root 24. Okay, so root 2 times root 24. Well, the square root of 2 is already broken down to its simplest form, so I'm going to leave it as root 2. And I'm going to take root 24 and break it down into root 4 times root 6. Now, the square root of 2 is root 2, and the square root of 4, well, that really is 2. And the square root of 6, well, that really stays as the root of 6. However, if I were to simplify further root 2 and root 6, I could do, I could put the 2 out in the front. So I'm going to put my 2 out in the front, and I'm left with root 2 times root 6. Now, if I reduce root 6 down even into its simplest terms, it would be times root 2 times root 3. So root 6 is like saying root 2 times root 3. And because root 2 times root 2 is really equal to 2, as I mentioned in class, then what I have here is a 2 times 2 times the square root of 3. And that ends up giving me nothing more than 4 root 3, which is the initial answer that we had at the beginning, except we did it in 2 steps or less. All right, let's take a look at the next example. Next example is root 12. And with the square root of 12, I could choose to do root 6 times root 2 or root 4 times root 3, but I'm going to choose root 4 times root 3 because the highest perfect square that I have is 4, so that I have 2 root 3. So if I try to do root 24 I could do as root 8 times root 3. I could do it as root 4 times root 6. It could be root 2 times root 12. But the only one of these that permits me to have a perfect square is root 4 and times root 6. So my best bet is to do root 4 times root 6, which equals 2 root 6, because the square root of 4 is 2. And root 6 cannot be reduced any further. All right, if we want to try to take now, let's take another example. So we've got root of 20. So if we take the root of 20, again there is root 2 times root 10, and then there would be root 4 times root 5. Well, the only perfect square that exists in here seems to be root 4 times root 5. So I'm going to say that the square root of 4 times the square root of 5 equals the square root of 20. And since the square root of 4 is 2, it goes to 2 root 5. If I take another example such as the square root of 42, let's take a look at 42. 42 could be broken down into 6 times 7, root 6 times root 7, or it could be broken down into root 21 times root 2. Well, neither of these have any perfect squares involved in them at all. Therefore, root 42 is already in its simplest form, in its simplest radical form. And if we take a look at root 45, well, root 45 is like saying root 9 times root 5, which gives us 3 root 5. Okay. We'll do a few more difficult questions. I already did them in class with the students, but let's do them again. So I would take root 25 times root 5 for 125, and you may use your calculator. And again, go up by the perfect squares. So start with, does root 4 go into 125? Or does 4 go into 125? No. Does 9 go into 125? No. Does 16 go into 125? No. Does 25 go into 125? Yes. And then I say that 125 divided by 25 is equal to 5. So root 25 times root 5 must give me 125. And therefore, the square root of 25 is 5. So my answer goes to 5 root 5. If I look at root 90, I know it's going to be root 9 times root 10, and that's equal to 3 root 10. And then my last example, root 9 is root 27, which is nothing more than root 9 times root 3, and that ends up equaling 3 root 3. Okay. Now, if I know what my simplified form is, how can I check to see if I did the correct simplification? Well, it's really quite simple. Let's go work our way backwards here. Let's take 5 root 5 and check to see if it's actually the simplified form of root 125. So the way we go about doing that is by saying, take the outer number and square it. So I take the outer number, the one that isn't in the square root, and I square it, and I say 5 times 5, and then I multiply it by root 25, by root 5, I apologize, so that I get 25 times 5, and that gives me 125. And then I just place it under the square root sign. Okay? So let's try the next one, 3 root 10. 3 root 10, I square what's on the outside of the radical, so I do 3 times 3, and then I multiply it by 10, so that gives me 90, and therefore my answer must be root 90, and that was my original question. Root 27, okay, is like saying 3 times 3 times the internal 3, and that gives me 27, and that means that the original question was root 27. So if I had an example such as 2 root 10, then, and I had to figure out what is 2 root 10, what was it originally before I simplified it, all I would do is I would take the 2, multiply it by itself, or I'd do 2 squared, so 2 times 2 is 4, and then I'd multiply it by 10, and that gives me 40. And then from there, I would place it under the square root sign, and therefore I know that root 40 is equal to 2 root 10 in its simplest form. So let's just take a quick look at these last 3 examples down here. So if I have 6 root 2, it's like saying 6 times 6. 6 times 6 is 36, times 2 is 72, and therefore our answer is root 72. If I have 5 times 5 times 3, that gives me 25 times 3, which equals root 75. And then 2 root 6 is 2 times 2 times 6, which equals 4 times 6, which equals root. Equals 24, and that equals root 24. Okay. All right, so there are 3 particular laws that I would like to go over. One of them being that a, the square root of a times the square root of a is always going to equal a. And now, that's one rule that you need to absolutely remember, in that the square root of any number squared is just going to be that number under the square root sign on its own, because what's actually occurring is that the squared and the square root sign are canceling each other out. Now, the second rule that I'd like for you to be aware of is that if I'm doing the square root of a and I'm multiplying it by the square root of b, I can actually place them both under the same square root sign, so it becomes the square root of ab. And therefore, an example of that would be, for example, the root of 3 times the root of 2 equals the square root of 6. So that would be an example. An example of the first one would be anything such as root 3 all squared equals 3, or root 8, no, not root 8, root 7 all squared equals 7, etc. Okay, our third rule is with division. So if I have the square root of a divided by the square root of b, I could really place them under the same square root, divide them first, and then take the square root. So for example, if I had the square root of 24 divided by the square root of 6, that would become the square root of 24 divided by 6, which equals the square root of 4, and the square root of 4 is 2. So these are 3 important rules that you should be aware of, okay, when looking at when we're looking at radicals. Okay, so we're just going to do a few examples. So a couple of examples would be something like this. So if I have 2 root 3 multiplied by 2 root 3, that means that I'm doing everything outside of the square root is being multiplied together, and everything underneath the square root sign is being multiplied together. So we have 2 root 3 times 2 root 3 becomes 4 root 9. Now, because we said that root 3 times root 3 is just going to equal 3, then I don't even need to put root 9, but I can just automatically write it as 4 times root 3 times root 3 is 3, so it becomes 12. If I do the next example, 5 over root 5 all squared, that means I square the top. 5 squared is 25. Root 5 squared is just 5, and 25 divided by 5 is 5. If I want to do 6 1/2 the square root, first I have to change it into an improper fraction, and the improper fraction is done by multiplying the whole number 6 times the denominator 2, so that's 12, and then adding the numerator 1 to it. So it's 12 plus 1 is 13, and it's 13 over whatever the denominator was. Now, because I can't take the square root of 13, and because I can't take the square root of 2, my answer just remains the square root of 13 over 2. If I want to solve 4 root 6 over root 24, I can do 4 and place them all under the same square root here, 6 over 24, which becomes 4 times 1/4. And now the square root of 1 is 1, and that gets multiplied by 4. And the square root of 4, down in the bottom here, is 2. So that becomes 4 divided by 2, which makes your answer 2. Now, an alternative way that you could solve this problem would be to do 4 root 6 over, and then I could multiply root 6 times root 4, divide this up, or simplify root 24, and the root 6's cancel themselves out, so that I end up getting 4 over root 4, which is equal to 4 over 2, and that equals still 2. So there's different ways. There's also other ways that you could approach this that works perfectly well also. Okay, I'm done. The only thing that I'd like to go over is maybe one question such as these ones, so write in simplest radical form. So if I have 14 minus, let's do the second example here, 14 minus the root of 50 all over 8, that would become 14 minus root 25 times root 2 all over 8. And that would become 14 minus 5 root 2 over 8. And that cannot be simplified any further. That's it. All right. I'm done, and I'll see you next time.